Today we are going to talk on a very important topic which is related with the top gas and thermal tracking. So today we are moving beyond just monitoring a gas to truly decoding the fauna's internal state. However, our focus is on the live data, the temperature, pressure, and top gas ratio that tells us exactly what is happening in the zones we cannot see. By tracking these variables in the real time, we can shift from reactive troubleshooting to proactive control, ensuring the furnace remains stable, efficient, and protected throughout every shift. So, the core mission is oxygen removal. Everything we do serves the core mission, that is, removing oxygen from the iron ore. We have two primary mechanisms. The workhorse is gas reduction, which remove about two-thirds of oxygen as carbon monoxide gas strip it away in stages. This process is efficient but stop if the gas cool below 500 degrees centigrade. The heavy lifter is the direct reduction, which handles the final third deeper in the furnace. However, direct reduction is energy intensive, as we all know. Our goal is to maximize gas reduction before the burden hits 1200 degrees centigrade critical threshold to maintain the peak efficiency. Now, the top gas reads the unseen direct reduction rate. Think of top gas as a live mathematical readout, not just exhaust. By comparing our raceway input like oxygen and nitrogen against the top gas output, we can calculate the direct reduction rate in real time. A high level is a win. It means gas reduction in the stack was highly efficient. Conversely, high carbon monoxide level mean unutilized chemical energy is escaping the furnace. We use this number to see the unseen chemistry occurring deep within the cohesive zone. Now, coming to the permeability bottleneck, the furnace speed is dictated by the permeability bottleneck. As we all know, to keep the process moving, blast pressure must accelerate gas to roughly 200 meters per second at the tuer. The ultimate resistance is cohesive zone, where softening ore create a barrier. To overcome these, the gas relies on the central coke chimney and alternating coke slits to ascend. We must remember that the fastest burden descent always occur exactly where the gas can create most voidage. Now, as you can see, the two profiles, that is the two signatures, we typically see two distinct flow, that is central working and wall working. Central working or the inverse V is our goal because it utilizes many active coke slits and keeps heat away from the shell. The wall working, the W shape, is dangerous. It forces gas to the wall, leading to high wall wear risk and vulnerability to water leak. As operators, we must recognize these signatures early to protect the refractory and maintain a stable flow. Now, coming to the reading of those radial profile, that is uh, above the burden. So to confirm our flow, we look at the radial profile above the burden. While temperature signature give us a hint, gas composition is the superior indicator. Specifically, look for the signature crossover in the center of the radius. If you see higher carbon monoxide percent combined with lower in the center, it confirms you have a strong centralized gas flow escaping through the coke chimney. These data tell us exactly how our internal inverse V is shaped. Now coming to the balancing the central flow trade-off. So there is a constant trade-off in the central flow. The benefit of central flow chimney is vital. It guarantees permeability and protect your walls. However, the cost is energy efficiency. If the chimney is too large, excess gas escape unused, showing up as high top temperature and wasted chemical energy. Your lever here is burden distribution. By adjusting the coke to ore ratio and carefully placing fines, you aim to maintain the smallest chimney possible that still ensures stability. Tracking the cascade of irregular burden descent. We must track the cascade of irregular descent before it becomes disaster. It starts with a hanging where the stock line stops moving because material is bridged in the stack. This leads to slipping, which is the sudden uncontrolled drop when that bridge finally collapses. Your primary real-time indicator for this is blast pressure. If you see erratic pressure variation while the blast rate is constant, the furnace is warning you of an impending irregular descent. And this also signify that it is going to affect our production very badly. So now coming to the high residual liquid choke permeability. So when cast house drainage is poor, high residual liquid flood the hearth, choking upward permeability. This liquid rise floods the void in the active coke zone, creating a massive restriction. You see an immediate rise in blast pressure and a disruption in your top gas ratio. The corrective action is immediate. Maximize drainage. In critical cases, you may even need to temporarily increase blast pressure to help push those liquid back down while you continue to the cast. Now coming to the low burden level, so which triggers a lot of thermal spikes. Losing your that burden level is a thus it becomes a major threat because it triggers massive thermal spikes. Without enough raw material to transfer heat into, ascending gas remains too hot. So if gas stay above 500 degrees centigrade without sufficient burden, chemical reduction stalls and heat is wasted solely on expelling moisture. You will see a rapid severe spike in top temperature combined with a chaotic changes in your top gas ratio. When this happens, when you must restore the charging rate immediately to capture that heat. Now defend the 90-degree centigrade top temperature floor. Now, as we have seen that one absolute optimal limit defend the 90-degree top temperature floor. Falling below this, avoid these are the basically a dangerous zone which are causing gas moisture to condense on internal steel walls. So this trigger water attack and refractory damage leading to premature capture failure. Whether you are refilling after a slip or during a blowdown, you must maintain top temperature above 90 degrees centigrade at all times to ensure the long-term health of the furnace shell. Now coming to the manipulating thermal state via tuyers. So we control the thermal engine via tuyers aiming for a flame temperature between 2000 to 2300 degrees centigrade. We have three main dials, that is fuel injected like coal or gas decomposes to replace coke. Blast moisture act as a coolant, effectively extinguishing excess heat if furnace runs too hot. Finally, blast oxygen directly increases combustion intensity to counteract cooling trends. So remember, lances must be perfectly centered to prevent critical water leaks into the raceway. Now coming to the operator's diagnostic translations matrix. This matrix is your quick reference guide for the converting signal into action. So if you see a central carbon monoxide spike, your chimney is too large. Adjust your chute angle. If you see rapid top temperature spikes, your burden is low. Restore the charging rate immediately. If blast pressure is rising alongside altered top gas, you have a high residual liquid. Maximize your drainage. So these chart ensure that every shift team respond to the same signal with the same high impact levers. Now coming to the proactive command loop. In conclusion, stay within the proactive command loop. Use top gas as your live feed for reduction efficiency and radial profiles to visualize the cohesive zone. Never allow liquid to choke the hearth and never let the top temperature drop below 90 degrees centigrade. The bottom line is this: you are not just reacting to alarm, you are actively managing a continuous high velocity chemical exchange. So, by using and referring those templates within the team in a single directional alignment gives a fruitful result in stabilizing the furnace in quickest possible time and run the furnace consistently.